Hello everyone, hope everyone is safe and doing good. Welcome back to my channel Trick or Treat with Mathematics. So in today's video, we will see the concept of Euclid's Division Algorithm and the concept of HCF and how these two are tied to one another. And without wasting any more time, let's jump right into the video. We have seen Euclid's division lemma in our previous video. And we know how we will be using Euclid's division lemma and the applications of Euclid division lemma to prove other statements. In today's video, we will see Euclid's division algorithm. There is a difference between these two. Before you understand the difference, you need to understand what exactly is the difference between a lemma and an algorithm. I have explained you in brief in the previous video. I'll link it up here. Division algorithm is used to compute the HCF of two numbers. And please do remember the difference between Euclid's division lemma and algorithm is Euclid's division algorithm is one more application of Euclid's division lemma. We will in today's video see how we can use Euclid's division lemma to compute HCF of or the GCD, that is highest common factor or greatest common divisor of two numbers, and how the algorithm ties together to compute the HCF. So what is the concept behind HCF of two numbers? Before that, we'll understand what exactly are common divisors. For example, I will take two numbers. I'll take 49 and 56. What is that common number that 49 and 56 is divisible? What is that common divisor? Is 49 divisible by 7? Yes. 56 also is divisible by 7, right? So that means the common divisor that divides both 49 and 56 in this scenario is 7. Can we not say that 1 is also a common divisor of these both? Definitely, 1 is a common divisor for all the numbers. That is, even prime numbers. That's the only divisor along with the prime number itself that divides the prime number. For example, if we take 7 and 5, what is the common divisor between these two is 1. Because 7 is divisible by 1, 5 is divisible by 1. In fact, any number is divisible by 1. Right? So, in here we have only one common divisor. Right? What if I take 32 and 24? We have many common divisors if you take these two numbers. For example, 32. In order to find the factors of 32, we'll write the factors starting from 1. That is 1 into 32. Then what is 2? What will we get the result when 32 is divided by 2? We get 16. And what 3 doesn't go in 32. 4 it goes in 8 times. 5 doesn't go, 6 will also not go, 7 also not goes, 8 will go again. So, but 8 is already here. So, we can conclude that these are the factors of 32. That is 1, 2, 4, 8, 16, 32. In the same way, let's try to find the factors of 24. So, 1 is a factor of 24, 2 is a factor of 24, 2 12s are, 3 8s are, 4 6 are. That's it. And then 6 4s are you get. So can we write the factors as 1, 2, 3, 4, 6, 8, 12, 24? Yes. So these are the factors of 32 and 24. In here, can we find the common divisors between 32 and 24? Common as in these two, they should be common numbers and we'll write them as common divisors here. So 1 is a common divisor. 1, 2, what else is there? 4 and 8. Right? Rest all are not common. So can we write the common divisors are 1, 2, 4 and 8. Amongst these, what is the highest common one? 8. This is nothing but HCF or GCD. The highest common divisors. If you write the factors and then take out the common factors and then write here as the common divisors, and if you take the highest common divisor, then we will get the HCF or GCD of those two integers. Okay, this is the underlying concept behind HCF and GCD. Keeping this concept in mind, let us now try to understand how we can apply Euclid's division algorithm to compute the HCF of two numbers. Now that we've understood the concept of HCF, the underlying concept of HCF in detail, let's see how we can apply Euclid's division algorithm, this algorithm, and compute the HCF by following these steps. The algorithm says that to obtain the HCF of two positive integers, right, he will say two positive integers as c and d with c greater than d, right? Why c greater than d? Because in here we are considering c is greater than d. One integer should always be greater than another integer to compute the HCF. If they are both equal, then HCF will be the same. So c greater than d. Then apply Euclid's division lemma to c and d. So we find the whole numbers q and r. Q is the quotient, r is the remainder, as I told you in the Euclid's division lemma. I'll be linking the video up here if you haven't watched. C is equal to dq plus r, we know that. So C is the dividend and Q is the D is the divisor. This is the dividend and this is the divisor in Euclid's division lemma, right? If R is 0, after we apply it, if R is 0, then D is the HCF. The divisor, whatever we get, H is the HCF. If R is not equal to 0, then what we need to do is, we need to pick up this R and pick up this D, and then D is the divisor here, R is the remainder, right? We get from first step, we need to compute the HCF on those two. That means you go back a step and then you put D in place of C and R in place of D, and then you compute. And we will stop when we get the remainder as 0. Until we get the remainder as 0, we will keep on doing this process. Okay, if you are confused by this, what we'll do is we'll try to apply it to two small numbers and then we'll progress our way forward. So, we need to find the HCF of 36 and 45 using Euclid's division algorithm. So, how do we find this? It's algorithm. So, how do we find this? Whenever you get a question like this, the first moment would be for you to identify what is the value of C, D, Q and R. So what is the value of C here? 45 based on this algorithm. What is the value of D here? 36, because one will be greater than the other. Q and R you need to compute. How do we get 45 as a result, and what are the values do we Q and R to get the 45 as a result here? Can we assume Q as 1 plus R as 9 to get 45 as the result? Yes, 36 into 1 plus 9, 36 plus 9 is 45. This is again in the form of Euclid's division lemma, that is C is equal to dq plus R. And what is R here? It's 9. R is not 0. If R is 0, then we can conclude that 36 is our HCF, but R is 9 here. So what we need to do? We need to go to the next condition, what happens when R is not equal to 0? Whenever R is not equal to 0, we need to apply Euclid's division lemma on D and R. Here D being the divisor and R being the remainder in the first step. So here what happens is, what is the divisor? 36, and what is the remainder? 9. So we need to apply Euclid's division lemma on 36 and 9. What will we get? Here the second one is 36 is equal to 9 into 4 plus 0. Can we write like this? Yes. So this will be C is equal to dq plus R. And in this case, R is 0. Yes. So what is the meaning of that? Whenever R is 0, the divisor will be the HCF. That is, in here the divisor is 9. So therefore, whenever we get R as 0 and when you compute the HCF between two numbers, the divisor in that step will be the HCF, highest common factor. That is nothing but 9 in this case. Okay. Using the division algorithm, Euclid's division algorithm, we can find the HCF in this manner. Now let's try to compute the HCF of 117 and 45 using Euclid's division algorithm. Now, first step of the algorithm is that we need to write this in the form of C is equal to dq plus R, so that 0 is less than R less than D. That is nothing but Euclid's division lemma. Now what is C here? 117 and D is 45. So So now we need to substitute the values in Q and R such that we'll get the result as 117. So what is the nearest value? Can you take this as 90 plus 27? Right? So can we say that 45 into 2 is 90, 90 plus 27 is 117? Because we don't have any multiple of 45, that will get 117 as the answer. Now, here we can say that this is C, this is D and this is R. And here R is not equal to 0. Until we get R is equal to 0, we'll keep on doing this process. Again, what we need to do? We need to apply Euclid's division lemma on D and R until we get the remainder as 0. So, we can say here as applying Euclid's division lemma on D and R. So once we apply this, we get 45 is equal to D and R is for 27. Can we take, so what will be the values of Q and R in this case, so that we'll get 45 as the result? It will be only 1. Q is 1, R will be what? 18. Right, so 27 plus 18 is 45. Again, if you observe, R is not equal to 0. In this case also, same thing again you apply. What will you get? 27 is equal to 27 is equal to 18 into 1 plus 9. Can you write it like this? Yes, because 18 plus 9 is 27. Again, if you see R is not equal to 0, again you apply Euclid's division lemma on these steps also. So lastly we get 18 is equal to what? 9 into 2 plus 0. Right? So here we get R as 0. So recursively, if you keep on applying the algorithm on D and R, applying the lemma on D and R until you get R as 0, you will be able to find the HCF. And here, since R is now 0, the HCF is 9. Therefore, the HCF of 117 and 45 is 9 by using Euclid's division algorithm. The next question is, using Euclid's division algorithm, we need to find the HCF of 4052 and 12576. So here, the first step is, you know that by applying Euclid's division lemma, we get 12576 is equal to 4052 into question plus remainder. So now 12576 is equal to, D is 4052, Q is 3, 4052, 3 is 12156 and the remainder is 420. So if we add, we get the value of 12576. So here the remainder is not equal to 0. So again you need to apply Euclid's division lemma. So what is applying Euclid's division lemma? You get it on the divisor. 20 into 9 is 3780. So if you subtract 4052 and 3780, you get how much? 272. So here the remainder is what? 272 if you observe. And the divisor is 420. Right? So now again the remainder is not equal to 0. So apply Euclid's division lemma. Third time when we apply this, we get 420 is equal to 272. You know for a fact that if you multiply by 2 also, you get more than 420. So into 1 plus remainder in this case is 148 and the divisor is 272. Again we'll see that the remainder is not equal to 0. Then the fourth step will be 272 is equal to 148 into 1 plus what is the difference between 272 and 148? This is the remainder and this is the divisor. Okay. Now 124 into 1 plus how much? 24. Right? And here also remainder is not equal to 0. Here also remainder is not equal to 0. See the number of iterations that we need to do to get to the remainder as 0 here. D is here. Take D is 124 and R is 24. Then we get 124 is equal to 24 into 5 plus 4 because 24 5s are 120 and we add 4. Here what is the divisor? This is R and again R is not equal to 0 here. What will we do? We'll apply this method once more. So then here the dividend will be 24 and this will be 4. Right? So here we get R as 0. So can we conclude that the HCF of 4052 and 12576 is 4 because R is 0 and the divisor of this step when R is 0 is the HCF. This is how you compute the HCF using Euclid's division algorithm. And there is an interesting observation here. If you see, right, let's take from the last step. If you see 24 comma 4 and what else we have 124 comma 24. I'm taking the combinations of dividends and divisors here. 148 comma 124 and then 272 comma 148, but 420 comma 272, 4052 comma 420, 12576 comma 4052. The common divisor of all these is 4. The HCF of all these subsets is also 4. It's still the common divisor. If you see here 24, 4, 124, the common divisor is still 4. Well, you compute for everything using Euclid's algorithm and you get the divisor HCF as 4. That's an interesting observation. This is the problem. A sweet seller has 420 Kaju Barfis and 130 Badam Barfis. I have underlined this for you because these are the key points that we need to consider. And she wants to stack them in such a way that each stack has the same number. That means in every stack there will be same number of Barfis. And they take up the least area of the tray. Least area. Here the word least is much emphasized. What is the number of Barfis that can be placed in each stack for this purpose? We need to stack these Barfis in such a way that we need to have less space in the tray. That means, in short, can we say that we need to put maximum number of Barfis in that stack in order for it to occupy or for it to leave less space, right? So how do you find the maximum number of Barfis? If you have 420 and 130 Badam Barfis that you can put on a tray so that it will be having very less space remaining. It's nothing but we need to find the HCF because it will give us the greatest common divisor between these two, and those many sweets it's the maximum capacity that a stack can hold, leaving less area. So that means, in short, we need to find the HCF of 420 and 130. So using Euclid's division algorithm, we know that C is equal to dq plus r. So 430 is equal to 130 into 3 plus 30. We get 390 plus 30 is 430. Again, it's not equal to 0. So we'll get 130 is equal to, this is r, it's d and r, 30 into 4 plus 10. Again, it's not equal to 0. This is d and we get 30 is equal to 10 into 3 plus 0. So here r is equal to 0. So the answer is 10. That means we need to place 10 Barfis in each stack so that they will be occupying least area of the tray. Okay, so this is how you use Euclid's division algorithm to compute the HCF on the problems. I would like to explain you one bonus concept wherein we will be able to find the HCF of 3 numbers if at all they ask you in any exam for that matter. You can use the Euclid's division algorithm to find the HCF of 3 numbers also. Okay, now let's see how to do that. Here, I want to find the HCF of 441, 567 and 693. What you need to do is, you first have to find the HCF of 2 numbers out of the lot. Any 2 numbers for that matter. Okay, then what you will do is, you will apply the result obtained after finding the HCF, right? After you get the HCF of these 2 numbers, for example 441 and 567, you will again apply HCF on the HCF of comma 693. That means first we'll find this as first step. We'll find the HCF. The result, if at all we get the result as 60 here, we'll find the HCF of 60 and 693, the remaining number. That's how we'll be able to find the HCF of three numbers. Now let's see this in action. First let's take these two as the numbers. So can I write 567 as 441 plus what is 567 minus 441? We get it as 126. Right, using Euclid's division lemma. Division lemma. Okay, next. Here the remainder is not equal to 0. So we need to keep on applying this lemma. 126 into 7, 378. 126 into 3 plus 3. Right? Again we can say that remainder is not equal to 0. This is divisor. Again, 126 is 63 2s are plus 0. So here the remainder is equal to 0. So the HCF of 567 and 441 is what? 63. Right? So now what we'll do is we'll apply 63 and 693 HCF using the same method, and then we'll find what will happen. It's the first step. Now the second step is you need to find the HCF of 63 and 693 because the remaining is 693. How do you do this? Using Euclid's division algorithm. So I will rub this here. So after doing this, we got the HCF of 441 and 567 as 63. Now let's try to find the HCF of 63 and 693 using Euclid's division algorithm. Now 693 is equal to 63 into how much? 63 ones are 11s are plus 0. Right? 63 11s are 693. So that means here the remainder is 0. So and the HCF is 63. So therefore, we can say that the HCF of 441, 567 and 693 is 63. This is how you find the HCF of three numbers using Euclid's division algorithm. First you pick two numbers of your choice, find the HCF and then get that result HCF and take this number and combine those two and find the HCF using Euclid's division algorithm. You will get this as the answer. Okay, so this is how you apply Euclid's division algorithm to find the HCF of three numbers, and also we have seen the HCF of two numbers in detail in this video. So I hope you understood the concept of Euclid's division algorithm. If you like my video, I request you to please like, share and subscribe to my channel and ring the bell notification down below so that you will never miss an update from me. I will see you all in my next video. Until then, I hope you have a safe day and a wonderful week ahead. Bye.